Hey everyone, so today we're going to be talking about the electric field. So what is the electric field? Well, it's the region around a charged particle where another particle feels a force. All right, so what does that really mean? Well, you know that like charges will repel one another and opposite charges will attract, and the electric field is what allows us to measure how that works. Okay, it needs to apply a force, right? But without touching, we use this thing called a field, similar to how gravity works, right? The moon stays in orbit around the Earth because we have this gravitational field. It's just a force that kind of permeates through space. You don't have to actually make contact. Electric charges work the same way, right? So in order to calculate the electric field, we use this equation right here. Okay, so it's E for electric field, force for the electrostatic force, that Coulomb's law of force that you learned about prior, and Q for charge, right? Sometimes you'll see maybe a little E right there, right? E equals Fe for electrostatic force divided by charge, right? So that's your equation right there. Pretty simple. They're not going to ask you too much more beyond that. And yeah, nothing really else to say about that. However, as with any physics equation, we need units. All right, so we have E equals, let me write this down over here. We have E equals F sub E over Q. That's not a Q. Over Q. Okay, now, what's the units for force? Well, if you remember, that is a Newton. Unit for charge is a Coulomb. So, the unit for electric field is a Newton per Coulomb. So just N over C. There's no special thing that you can kind of replace that with. It's just an N over C, newtons per Coulomb, however you want to look at it. Okay? All right. So that takes care of the magnitude side of electric field. But it's important to know that the electric field is a vector, which you should remember also needs a direction. Right? Now, how do we manage the direction of an electric field? Because if you were to do an experiment, you would see that there are no arrows anywhere. They're just lines that you can kind of measure their intensity, but there's no arrows. So how do we turn this into a vector? Well, scientists way back when created a convention that the electric field will point in the same direction that a positive test particle will move in the presence of the charge you're looking at. So let's take a look at this. I have here a positive charge. This could be a proton, an alpha particle, some other miscellaneous particle that has a positive charge. Could be, you know, a positive ion of some element, whatever, just some positive charge. Okay? Now, if I were to take my little test particle right here, okay, what direction would this particle move because of this particle? Well, it would move up. Okay, if I were to move my test particle over here, it would move this way. Okay, if I were to put it right here, right, it would move that way. And if I were to put it out here somewhere, it would move that way. And here we go. Here we have a properly drawn electric field diagram for a single positive charge. Okay, now take a look at this. Take a look at what you see here. Right, there are certain things about how this is drawn that you have to make sure you take care of in order to get the full credit for whatever you need to do. All right? There are 5 rules that go with it. So let's write those down. Okay, so remember that picture. Hopefully you wrote it down or something like that. So let me write 1, 2, 3, 4, 5. Okay, there's no particular order. It's not like you have to do 1 in order to do 2. I'm just going to put these in an order. So rule number 1, just for my personal list, is going to be they must have arrowhead. Right? I know it's kind of messy over there, but it must have an arrowhead. Without an arrowhead, you can't establish direction, and direction is very important when you're trying to determine the direction. Right? Makes sense. Okay? So one of those things is it must have an arrowhead. Okay? Another one is it must touch the particle. All right, so when you're drawing your electric field lines, you've got to make sure that the lines actually make contact with the circle or whatever picture it is. Sometimes you'll see it's a bar, which we'll get to in another video. Okay, so must have an arrowhead, must touch the particle. Okay, a third rule would be that they must be at least 4. Right? You have to have at least 4 lines. Sometimes the question will say 3, sometimes it'll say 5. Usually it's 4. Stick with 4 and you're good to go. Okay? The next rule is much like the proton packs from the Ghostbusters, when they're not trying to fight Zuul, is they cannot cross. Okay? The lines can't cross. The way they're drawn is for a circle particle like that we saw before, is they're drawing essentially perpendicular to any tangent you can draw on that circle, which would make them perpendicular, and they just can't cross. They're just not anything that crosses. And the 5th rule, and this one's kind of wishy-washy a little bit, we'll get to that part in a little bit, but this is a pretty standard rule, and the 5th one is that they must be straight. Okay, so here are your 5 rules. Must have an arrowhead, must touch the particle, must be at least 4 lines, the lines can't cross, and the lines must be straight, right? You can't have any wavy, wiggly lines, right? It's just not how it works, okay? All right, so hopefully you got this down. I know my handwriting's a little rough, but I've kind of narrated them as I wrote them. So we saw how a positive particle works. Let's talk about a negative particle, right? Because we know, obviously, that those exist. So let me draw my little negative particle. Here we go. Okay, now, again, it's always the direction a positive test particle would move. So if I put a positive test particle here, where would it go? Well, positives would be attracted to a negative, so it would go that way. Notice, it's a straight line with an arrowhead that touches my particle. Okay? Here we go. Here we go, right? Because if I put a positive particle here, it would be attracted. If I put a positive particle here, it'd be attracted. If I put a positive particle here, it would be attracted. Okay, so here we go. I followed all 5 rules. They touch the particle, they have arrowheads, they don't cross, they're straight, and there's 4, right? A nice negatively charged electric field. Okay, awesome. Now, obviously, we can get scenarios where there are more than one charge at a time. So how does that look, right? So let's take 2 particles. Let's say in this particular scenario, there are 2 positive charges, right? Again, 2 protons, 2 alpha particles, 2 positive ions, whatever. Now, as always, where is that positive test particle going to move in the presence of these? Well, if I put it here, right, well, it's going to go out this way. If I put it here, well, it's going to go out that way. If I put it here, well, it's going to go out this way. Same thing on the other side, right? If I put it there, it's going to go out. If I put it there, it's going to go out. If I put it there, it's going to go out. Now, the important part for a scenario like this is the middle, okay? And this is where that kind of must be straight rule gets a little wishy-washy, and you'll see that in a second. If I put a particle here, that positive test particle right here, okay, it's going to be repelled by this guy, but as it gets further and further from this one, it's going to get closer and closer to this one, which then this one will start to repel it a little bit more. So you end up by taking this infinitesimal amount of vector additions to get kind of a curvy line here. Notice how it's not wavy, it just sort of curves as you get closer to the other particle. Again, this looks like it breaks that rule, but really what it is that every single point, which is an infinite number of points, you just have a little bit of force here plus a little bit of force here, so it ends up looking like this. And as you add all those points up, it looks like it curves. All right, so then the same kind of thing down here, same kind of thing down here. So here we have the electric field diagram for 2 positive charges near each other, right? Around the outside, it's still that radial kind of look, but then the inside, which again is the most important part, they kind of curve away from each other. All right, cool. So let's take a look now at 2 negative charges, okay? 2 negative charges. Okay, we know again they're going to repel, but how's that going to look for our lines? 2 negative charges. Well, If I put a positive charge here, it's going to attract. Positive charge here, it's going to attract. Again here. Again here. Again here. Again here. And once again, the most important part is what happens in the middle. Well, if I put a positive charge here, it's going to be attracted a little bit by this one, but a little bit by this one. It's a little bit closer to this one from right here, so it's going to kind of curve in. Same thing here. Same thing here. Same thing here. Right? Very similar to a positive charge scenario, but just now it's pointing into the charge because it's a negative charge and it's always drawn in the direction that that positive test particle will move. Okay? All right, and the final scenario that you will need to know about is what happens if there is a single positive and a single negative. So let's draw that right here. All right, one positive charge, one negative charge. All right, well, again, where's that positive charge going to go? From right here, it's going to go out. From right here, it's going to go out. From here, it'll go in. From here, it'll go in. Okay, ooh, let me make that better arrowhead. Now, once again, the middle part is the most important piece. If I take it here, it's going to be repelled. But as I get further from this repulsion and closer to this attraction, it's going to kind of curve around. Similar kind of thing on the other end. And in the middle, it'll just go straight through. So once again, this is a properly drawn electric field diagram. This time it's for one positive and one negative charge. Okay? If you notice in all these cases, and it's just based on that definition that it's where a positive charge would move, the electric field always points from positive to negative. So away from positive toward negative.